the other technicians.
Welcome back after lunch. So I'm going to talk about single agent dynamics, and I'm literally going to start talking about a single agent, this guy. Okay, this is Harold Zucker, the superintendent of maintenance in a bus company, and this is a guy we're going to model. And John wrote a paper about him in 1987. Rust, not to be confused with Matthias Rust in 1987, the Rust 1987. It's called Optimal Replacement of GMC Bus Engines in a program model of Harold Zucker. Okay, so this is actually a pretty path-breaking paper. So it introduces a technology that allows us to estimate dynamic discrete choice models, also more generally. And so the main contribution here is that he has this illustrative application of this guy you saw here, and a model of how he would optimally replace engines in his fleet of buses. Okay, so then how does he do that? Well, he develops a method. It's called the nested fixed point algorithm, or an algorithm that allows us to implement the max likelihood estimator for this model. Okay, so I'm going to talk about the nested fixed point algorithm. Okay, so and how is that made feasible? Well, John, he formulates a set of assumptions. I'm going to reuse some of those as well. That allows us to specify this model in a tractable way, so we can easily write up the likelihood functions and the Bellman equations in a more or less more tractable way. Okay, so then you obtain some max likelihood estimates of this model and use it for counterfactual simulations. And one of the other things that's there too is that he's creating this bottom-up approach of micro-aggregated demands for durable assets like bus engines, and then you can track out based on the implication of this model the demand curve, how demand for engines that varies with the price, which is the replacement cost. Okay, so then you do this various counterfactual experiments with this model. Okay, so you might ask, who's going to care about Harold Zucker? Okay, this guy in this bus company. Well, there's a lot of people who got inspired by this kind of work, and generally it's discrete choice modeling, right? So you got occupational choice, you got retirement, you got brand choice and advertisement, choice of college major, all these discrete choices, residential work location, fertility, and whatnot. Okay, so all this stuff is kind of, Harold Zucker and steroids, okay? And later this week, we're going to hear about optimal replacement of kidneys. It's kind of also like an optimal stopping problem. If I'm on the wait list, should I really accept this kidneys coming now, or should I wait for something better coming up? Okay, so details, I guess you're going to talk about that. And then later, if we have time, we're going to talk about a more recent paper that we're working on, or is done. It's published. It's going to come out in the JPE this after the summer about equilibrium trade in automobiles. Okay, so and there's much more than this. Okay, so then there's. So I'm primarily going to talk about the nested fixed point algorithm in this talk. Okay, so that's Rust 1987, but there's a wide variety of various different methods to estimate a model like this. And Bob is going to talk about the CCP methods and various variations. And today, I'm going to also talk about something called a mathematical programming with equilibrium constraint, which is kind of a constraint optimization approach to structural estimation of these kind of models. Okay, so this is what we're going to focus on today. Okay, and you say, okay, there's all these algorithms. Well, what you usually do is, when you come with a new algorithm, you use the circle model as a test bed to see if can you confront your circle with your model, and does it fare better than previous methods? Okay, so anyway, and it's a kind of an old paper, but people are still reading it. Okay, this is a citation curve for Rust 1987. And the R squared here is very close to 1. Okay, so it's a simple quadratic, which kind of means that it's just constantly growing over time, and every year the citation growth, annual citation increases linearly. Okay, so this is almost like a policy invariant structural parameter, constant growth of this Big Mac index of structural metrics. Anyway, I think we've settled to talk about formulation, solving, and estimating a dynamic model. Okay, so we're going to start with some of the primitives. It's decision variables. People here make discrete choices. We're talking about discrete choice model. Okay, so they make a discrete choice D that can come from some state-dependent choice set. Okay, so like a finite number of alternatives. Then there's going to be the state variables, and the state variables is all variables that describe all the relevant information about them by the agent's decision process. Okay, so enough to make predictions about how that develops in the future. And then there's going to be utility functions or cost functions, some instantaneous payoff that the agent gets. That's dependent on those states and dependent on those decisions. Okay, and then we have time separable utility. Okay, and then the agents, well, they make beliefs about how those state variables evolves over time, and we assume here that follows a Markov process. Okay, so we call that process P here. That's the distribution of the future states conditional on the current states, and how you affect that transition by making discrete choices. So, Harris-Zucker is talking about replacing engines. So if I replace the engine today, well, the distribution of the mileage on that engine is going to be different tomorrow because, compared to if I didn't replace the engine, it would have all that accumulated mileage since the last replacement. So you can affect the future distribution of the states by these discrete choices. And then the solution is given by the value function, which is kind of the maximal attainable utility from now on into the future, and then the policy function, which kind of gives a mapping from the state space to the action space. And what we want to do is we want to estimate the models. We want to, and how do you do that? We parameterize usually the utility function, the motion rules for the states, the choice sets, the primitives of the model, and then we take it to the data and try to, find the parameters that fits the targeted moments, okay, or it maximizes likelihood. We're going to do maximum likelihood today. Okay, so here's Harris-Zucker. Okay, so we get a binary choice. Okay, I should turn around here. So we've got a laser. Got a binary choice, 0, 1. Replace is 1. Okay. 0 is just doing ordinary maintenance. And then the state variables, well, this is what Harris-Zucker observes. He observed the state variables S, okay? It composed into two things. The mileage on the bus since last replacement is growing unless you replace the engine. And then some epsilon shocks. The epsilon shocks are like idiosyncratic shocks to investments or taste shifters. Okay, so if the bus comes in and smoke all over the place, for some reasons that is not captured by that state variable X, well, you got a shock to reinvest in that engine. Okay, and then you got a utility function here. So if you are not replacing the engine, well, you have to pay the maintenance cost. Okay. The maintenance cost is a function, it's increasing function of the age of the bus, or the mileage on the bus. Okay, so it's going to be, as it approaches kind of the conger state where it's just driven so many miles, then it's going to be more expensive to do maintenance all the time. Right? You have to, place gaskets and bearings and all this kind of stuff. Okay, or you can just replace the whole thing, in which case that state regenerates to 0, and you pay essentially only the replacement cost, and then maintenance cost of a brand new bus. Okay, so here the state variable process, the motion rule. Well, those epsilons there have this conditional density. Okay. And then we have the mileage process, which essentially is a regenerative random walk. So you replace the engine, then the bus just regenerates to 0. Okay, so brand new bus. Okay, number of miles since last replacement is just 0, and then there's a distribution of how much the bus is driven within a period that determines what the distribution of mileage is in the next period. Okay, and then we want to estimate the parameters. We're doing structural estimation. We want to estimate those replacement costs, the parameters that enters into that utility function or the cost function here, and then potentially also the parameters that enters into the state transition process. Okay, so what is Harris-Zucker doing? Well, he's choosing a sequence of actions, of replacement actions, every single period, right, in order to maximize the expected discounted utility over a, in case of Harris-Zucker, an infinite horizon. Because we're going to focus on infinite horizon problems here. So he can solve that recursively by the Bellman equation. By the principle, Bellman's principle of optimality. Then this is this value function you have right here. That is that's a solution to this Bellman equation. You see immediately here, right? You got this value function of both sides of this equation here. So you need to find a fixed point on the functional equation. How do you get that expectation? Well, that's a double integral over the observed states and those Myrick states, and then also these epsilon shocks. Right? Now you look at it directly here without making any further assumption. It's kind of actually pretty hard to compute. Well, think of a bigger model where there'd be more state variables and more multinomial choices and so on, right? There are some challenges. Okay, now X here is a continuous variable, epsilon is continuous and J dimensional, just J alternatives. Okay, so you need to do that makes this function here, which is solution to the fixed point equation here, a potential high dimensional object. Okay, especially because of these guys here. Okay? So if you have like 10 alternatives, you have like a 10-dimensional state vector. So evaluating that expectation may require high-dimensional integration. Well, you could do simulation, but you still need to be able to evaluate the value function in each of these values of epsilon. So that may require high-dimensional interpolation or approximation, and so that's challenging too. Okay, the function is non-differential because of discrete choice. So there's a potential amount of challenges that we are meeting when we look at models like this. So what I'm going to do here is I'm going to list all these assumptions that John made to make this tractable in 1987. Okay, so here the first one is that the epsilon shocks that enters into utility is additive with sequel. Okay, so you have the first part of utility that only depends on the mileage, okay, or the absorbed state variable, whereas the last part here is just adding additively is something that shifts up and down utility. Then there's a conditional independence assumption that gives us the motion rule. The motion rule follows this control macro process with a probability density that factors into these two terms. Now, what you notice here is that epsilon that we condition on here is not appearing in any of these two. Okay, so this, for example, rules out zero correlation of the epsilon. So intuitively, you think of this as epsilon, since the noise is superimposed on the problem. You can go further and assume that these epsilons following this distribution function. So it's I at the extreme type 1 value, and we already heard this morning that's going to give you Logi formula. Okay, it's going to give you Logi choice probabilities. And it's also going to give us closed form for the expected max. Okay, so let's take the Bellman equation again. Okay, and let's see what all these assumptions is doing to it. It's because it's going to simplify. Okay, so the first thing, the additive, the additive separability and the conditional independence is going to allow us to separate out the deterministic part of the deterministic part of the choice-specific value, so that we can actually reformulate the Bellman equation in a much reduced state space, and I'll show you how to do that. Okay. And then with the extreme value assumption, well, you got closed form solutions for expectation of the max and for the conditional choice probabilities. Now, you can still have those assumptions and put more stuff into your model, like we saw with the mixed logit, for example. You can have an additional random component if you don't like that extreme value assumption. But then you have to add it into to X. I'm not going to do that right now. Okay, so here's the dynamic programming under the additive separability and conditional independence assumption. And we just moved a little bit around here in the Bellman equation. What you see here is that this whole part, well, that does not depend on epsilon because of the conditional independence assumption. It's essentially just we can integrate it out. It doesn't depend on the current value of epsilon. It only depends on X and decisions. And then you got epsilon here right at the end. Okay, so this means that we can write the value function here as the maximum, this choice-specific value function before the arrival of the epsilon shock, then plus the epsilon. Okay, where this is, yeah, you got the formula right there. Okay. Okay, now we can express the Bellman equation in expected value function space and just work with the expected value function instead. Now, we take the expectation of our value function conditional on the state variables and only these observed state variables X in the decision, and that's going to be a function only of those two variables. We can integrate out those epsilons. Okay, so if you do that here, do that expectation, that conditional expectation, well, you get a mapping from expected value function, from expected value functions to expected value function. This guy here, it's written out down here. Okay, now this is much lower dimensional. Right? Remember the discrete choice model with Mermin alternative, you would have many epsilon shocks. They're no longer there. Okay, so you can solve this Bellman equation instead, and then that lives on a much reduced state space. It is still a contraction mapping, and you can find the unique fixed point of that Bellman equation using standard methods like successive approximation or doing contraction iterations, where you start guessing on a expected value function, throw that right in here, and then you recalculate that new guess. Well, you put that right back into the Bellman operator, iterate, and then it converges to this unique fixed point. That's what you get out because it's a contraction. So you got global convergence of value function iterations. Okay, and it's lower dimension. Now, you can also work with something called the integrated or smooth value function. It has many different names. So here we call it integrated value function, where you only do the integration over that value function as a function of X and epsilon with respect to those epsilon shocks. Okay. So that's what we have right here. Again, now you got another Bellman operator on an even more reduced state space on this integrated value function, which is only a function of the state variables X. Okay, so you got a mapping from these integrated value function to integrated value functions. Again, as a contraction, you got global convergence, all the nice properties we had before. Okay, so let's take assumption number 3, the extreme values. Well, Still need to calculate the expectation of that max, but with the extreme value, you got closed form solution for that expectation of the max. Okay? It's called the log sum. And that is just much simpler and much more numerically well behaved than computing that expectation using the integration over the epsilons, evaluating that max of that's non-differentiable function for all your simulations. You just do the log sum. Okay, computational advantage. Okay? Really cool. Now you got to get the choice probabilities, just like Whitney said, is going to have closed form choice probabilities here. Now, of course, everything depends on the choice specific value function, which in itself is functions of this expected value function or integrated value function. So still need to solve the functional equation. Okay, but this is huge benefits, right? It avoids the j-dimensional integration over the epsilons to calculate the expectation of the max and the choice probabilities. And then on top of this, these objects, the conditional choice probabilities, the integrated value function or the expected value function, they're all smooth objects. Okay, you change parameters a little bit, well, they're going to change smoothly. Okay, so this is very nice properties. Makes empirical work all the more easy. Okay, so put all this stuff together. Then essentially you got your conditional choice probabilities. You can calculate those using the Loescher formula. Here, what enters here is the expected value function. Well, you still need to calculate that fixed point in order to get that from that Bellman equation. Okay, now what you should, what we do here is we do a little subscript on the Bellman operator to with the theta to emphasize that everything here depends on parameters. And you can easily see it, right? You change parameters here, well, that changes that mapping, right? If it changed the Bellman operator, well, the fixed point is going to change too. So that's a function of the parameters too. It's like an implicit function of the parameters. And so, you know, if this is a function of parameters, well, the conditional choice probabilities, they're also a function of the parameters that we want to estimate. Okay, we're not quite there yet to the nested fixed point algorithm, but we'll get there soon. But you can imagine that these conditional choice probabilities, they will enter into the likelihood function, and every time you calculate the likelihood function, you would have to solve that fixed point in a kind of nested loop. That's why it's called a nested fixed point algorithm. Okay, well, Matrices continues. There's many ways to deal with this, you know, Chapter polynomials, and you know, various types of approximation methods. Okay, splines, whatever you have. Okay, we're going to do discretization, very simple. Okay, that's what John did in his paper. Okay, this means that once you discretize the state space and the distribution of this macro process, also become a finite state macro process, and it's completely governed by two sets of transition matrices, one if you replace and one if you don't replace. They look like this. Okay, so here is the transition matrix for Matrices conditional on keeping the engine. Okay, now these are essentially the probability for going from, say, the first state here. You got all the states that say discretized into 100 points, right? So you got you know, brand new engine here, very old engine here. Okay? So this is a probability of staying in the same new engine. Okay, this is a probability of moving up another interval in your discretization. And at some point, you're going to stop having positive probabilities, because if the state space, say, go from 0 to 500,000 miles, the zero probability you drive like, you know, 100 times around the world within a month. Okay, so some of these probabilities is just set to 0. Okay, and you're not driving backwards either, right? You know, it's a bus. Okay, it's supposed to bring people forward. Okay, so we have this assumption. Now, the state can actually move backwards. Okay? You can get a newer engine, right? If you replace. Okay, and then the mileage transition matrix looks like this. Okay, so you wake up in the morning, you replace the engine, that goes to 0, but then it drives according to the same distribution every month, and then there's the same probability of going to staying in the same state, moving up 1 bin, 2 bins, and so on. Anyway, these are Markov transition process probability matrices, and they depend on the discrete choice. Okay, kind of control Markov transition matrix. Okay, so then we can easily implement this on a computer. Here's the Bellman equations of the two sorts we looked at in matrix form. Okay, you got it for the expected value function, you got it for the integrated value function. This is really something you can implement on a computer. And by the way, there is code on GitHub or in the box or wherever you get the teaching material for implementing this Bossinger replacement problem and for replication of the results. I'm going to not run simulations, but I have some results for you. You can check them out. Like there's a code called run bus data that replicates the results. So check that out. And all these equations you're implemented there. Okay, so here you got utilities, expected value functions, integrated value functions, just stacked across all the different points in the state space. And then this is very easy to code. Okay, now we want to do estimation. Okay, so we have data on discrete choices, B, observed for each of the buses at different time periods. And then you got the mileage observations. Here I've written like you have panel data. Actually, you don't really need a whole panel. You need to know what the mileage of the bus and how much was it driving. Okay. So you can identify the state transition process. Anyway, that's a detail. Let's just assume we have this panel data. Now, what you want to do is you want to maximize the likelihood with respect to those parameters. But recall that those expected value functions that enters in here implicitly in the conditional choice probabilities that we have the formula here for, this expected value function, well, that changed too when you change the parameters. Okay. So for every time you evaluate the likelihood function and calculate the choice that involves calculating the choice probabilities, you need to find the fixed point of this Bellman equation, or analogously find the fixed point of the Bellman equation in integrated value function space, which is equivalence. So that's what we do. Here, in a more abstract way, you can say, okay, nested fixed point algorithm is solving this unconstrained optimization problem. It's maximizing that likelihood function. But every time you evaluate the likelihood function, you also have to solve the fixed point and get that expected value, which is recalculate that expected value, which is an implicit function of the parameters. How do you do that? Well, you do an out-of-hill climbing algorithm that search over the parameter space. That's the replacement cost, the utility cost parameters, transition cost parameters potentially, although you can estimate those in the first step by not without even solving the model. You do that, you search over, but and in order to search over the parameter space, well, you can use your favorite optimization algorithm. Okay. I recommend that you do that like John did and wrote down his documentation manual, use the so-called BHHH algorithm. Okay. Now, we had about maximum likelihood this morning. One of the things that I think Whitney, or maybe I was doing something else, but Whitney didn't say so much about is the information identity. So you can actually approximate that Hessian with the outer product of the scores. That's the idea you're using the BHHH algorithm. Now, anyway, I'll show you. Each evaluation requires you to solve the fixed point problem. How do you do that? Well, you can do successive approximations, Well, it turns out to be really, really slow, especially in betas close to 1. So you can also solve it using Newton's method, or using Konchurovich iterations, if you think about it in function space. Okay, well, you got the data by Harris Zucker and his record of all the buses. He has all the observations on mileage and replacements, and that happens every month. And he is focusing on these discrete choice of whether to do maintenance or replacement. Okay. So here's the data, okay? And you can estimate a discrete choice model.
Can I ask a quick question? So I usually give my PhD students the recommendation to use a CAN optimizer from whichever, like Julia or whatever else, rather than code up their own optimization. What do you think about that?
That's also what we do is we in the code that you have here is we're not coding up the optimizer itself, but the optimizer is relying on first and second order derivatives.
Yeah.
And so one way to really speed up things is to use the information identity to approximate those second order derivatives by the outer product of this force, and then supply that to your CAN routine. Okay. So yeah. Anyway, so you can estimate this model, and here's a prediction from the dynamic model and for the static model. So I'm not going to go so much into the empirical results of Charles Zucker. Well, just say we can, we get parameter estimates. There's various different groups of buses. There's some heterogeneity across the cost and the replacement cost and the maintenance cost parameters, how much they're driven and all that. But these parameters are estimated by the fixed point algorithm. So it's our parameter space repeatedly solve the Bellman equation. We can do that as well. Okay, it's called run bus data, and there's no way I can cover all the details of the code. But actually, try to go into the code and make it like a one-to-one translation from the equation you see on these slides, and then see if you can discover these various functions in there. Okay, so the code replicates essentially what we saw in this table. Okay, so I think it's bus groups 1, 2, 3, 4. So it better be close to that. Okay. Now you can also do this bottom-up approach and calculate the equilibrium mileage and demand for engines. I'm going to fast forward because I want to get some time to John. So just saying that you can find that equilibrium distribution as another fixed point to find the fixed the ergodic distribution to this macro process, control macro process. In fact, we're going to do very similar things with this this bigger model on the Danish farmer. Okay, so MPACT. MPACT is used for many other things in estimating dynamic discrete choice models, also for random coefficient local demand modeling, and for estimation of dynamic discrete gains of incomplete information. There's a bunch of references here. I'm going to skip that. Okay, now let's just dwell with the nested fixed point algorithm for a second and compare it to MPACT. Now, Nfxp is solving an unconstrained optimization problem, treating the expected value function as this fixed point as an implicit function of the parameters. Every time you change that, you need to update the fixed point. It seems like a lot of work. So what Sue and Judd, they suggest is, why don't we just maximize the likelihood function, not only with respect to the structural parameters, but also these expected value functions. So you have 175 grid points, you have 175 additional variables in this constraint optimization problem. Okay, I mean, remember this guy here, you treat that as a variable, you can maximize this thing. You know that's this expected value function. You have that variable, you're searching over it together with the structural parameters. Well, you need to make sure still that it's a solution to this equation, the Bellman equation. So what they do is they impose it as a constraint and use a constraint optimization solver. Okay, so we end with something like this. So you maximize this likelihood function, treating both the structural parameters and the expected value function at each point in the state space as variables in this constraint optimization problem, imposing the constraints that the Bellman equation needs to hold in all the state points. And it only have to hold at the converged value. It doesn't have to repeat every time you evaluate the likelihood function. So it looks like it could be much, much faster. Okay, so they have in their paper two different implementations. They have one they call MPEG ample that's implemented in some high-level software, just like if you know, have you done any, computational or computable general equilibrium models, you'll know GAMS. It's very much like GAMS. Okay, so there's constraint optimization solvers. You just need to specify what a constraint optimization problem is. In ample is doing a lot for you. It's doing automatic differentiation. It's providing sparsity patterns for the Jacobian of the constraints, the Hessian of the likelihood. Okay, in a very easy way. You can also do it in MATLAB. Well, you would need to supply these Jacobians, the Hessians, and the sparsity patterns yourself, but it can be done. Su and Judd, they are not supplying the second order derivatives. That's a lot of work. And then they test these two implementations against each other. Now, key success for implementation is actually you really use these sparsity patterns. Okay, here's the map of the Jacobian of the constraints. Remember the constraints of the Bellman equation. You've got a constraint for each point of the state space. You'll have 175 grid points, right? And then you want to have the derivative, so you can do the border Hessian to your constraint optimization solver. Right, and so in this case, it's 175 times the number of parameters, which is 175 plus these 5 structural parameters. It's 180. Now, computing all those derivatives takes potentially a lot of time, but you can see many of them are 0. Okay, all the white space that's 0. So if you tell the computer where not to look for calculating derivatives, you're going to save a lot of time. Most of the space here is 0. Same thing if you look at the second order derivatives. Where does that come from? Well, it comes from the sparsity of the transition process in this case. So this is potentially powerful when you're working with a transition equation where you have some sparsity patterns. Okay, now actually. This part, not worrying about the structural parameters of the first one, but the values of the expected value, this is the derivative of the Bellman operator. Okay, and really what that is just choice probability weighted sum of these matrices here, which is why it looks like that. Anyway, there's some details. Let's look at how that works. Okay, so Su and Judd, they did a Monte Carlo, a little horse race on the Harrow-Sucker problem. They were looking at buses 1, 2, 3, and mimicking the parameter settings that there was in that table 10. I think it's in the paper. Okay, so you got the fixed point dimension of 175. You got 175 grid points, and we got this linear cost function. We want to estimate theta 1. You got a Meilerich transition that allows you to only move up 4 points. And that's just determined empirically because nobody in the data is moving up more than 4 points when you discretize in 175 grid points. Here are the parameters. You got the slope parameter here, it's 2 point, it's not colon, 2.2, whatever. And you got the replacement cost around 11. And then you got the parameters that index the motion rho for this for mileage, which is these 4 probabilities that you saw in this matrix right here. Now it's going to be 4 of them. So on. So these are the parameters. Let's go back. Okay, we're right here. Okay, so what they do is with these parameters, we can solve the Harris-Sukker's model and then simulate from this model monthly data for 10 years and 50 buses, which is kind of the same sample size as John was using. Here are the results. You got the MPEG ample, you got the MPEG MATLAB. Now this is using the second order derivative, so expect it to be faster. And you can see here, you look at the computer time, it's 0.1 second. It's it'll be faster, it'll travel back in time. Okay. MPEG MATLAB, well, it's not using the second order derivative, so you have to use some sort of, do some part of this numerically. That takes more time, okay? and so that's expected, okay? And then you got Nfxp. Well, it's kind of old, right? So what do you expect? It's from 1987, so it can't be fast. Okay, and it gets worse. So you look at it. Look at the computer time, you have got beta equal to 0.995. You got almost 2 minutes of computation. And if you look at the times it converts out of the 1250 times we're looking at it, it's not really working all the time. It's a little bit discouraging. Look at how many contraction iterations you were doing during the course of estimation. How many times you have to evaluate the Bellman operator? 748,000 times. Okay, took almost 2 minutes to estimate Harris-Sukker's model. What John did in 1987. Okay, so you look at this and say, can this be right? Can we do something? Okay, maybe we can. Okay, so here's a survival kit for Nfxp. And so it's not so much about MPEG, it's mostly about Nfxp because implementation matters, okay, how you do this. And you'll see it. Okay, now the first thing you want to do is read the manual. Okay, that's a very nice manual that John wrote back in 85. I have a version that's a little bit later for 2000. I can link. You need to also think about implementation of Loci formulas and lock zones. It turns out that they can be numerically unstable, especially when beta becomes very close to 1. It's like you're discounting the future, but you put a lot of weight on all that infinite future, so these values becomes very big. Then you need to not use only contraction iteration or successive approximation, not only SA for successive approximation, also Newton. Okay, and it turns out that Suijad, we're not doing that. That's a part of that explanation. It becomes even more important when beta was close to 1. You got to provide also analytical gradients for the Bellman operator, calculate the analytical gradients of the likelihood function to really make Nfxp work fast. Okay, and then you need to use the information identity and post that structure that we know is this maximum likelihood to use the outer product of the gradients as a Hessian, as an approximation to the Hessian. So let's see if we can go a little bit, through some of this. I'm going to at some point just skip over the rest, but it's in the slides. Okay, here's some links to documentation, the original paper, the documentation manual, and then we have a comment on Suijat's paper. In the documentation manual, actually, this is a version 6 from 2000. John actually recognized you could do this as a constraint optimization problem. Okay, so he thought about that at the time. But he's not doing that. He's actually advocating for doing the nested fixed point why not use the structure of the problem that you have a contraction mapping that's really giving you good convergence properties because you have a surefire way of finding the fixed point, okay, if you were patient enough. Then there is the Nfxp pocket guide buried in there, okay? That gives a complete overview of all the things you have to remember in order to do the nested fixed point algorithm. Okay, you start with some initial value guess of the value function and an initial guess of the parameters. What you do then is you do a contraction iteration. You know, put that guess into the Bellman operator, update that. You iterate on that until it's sufficiently close. We'll talk about what sufficiently close mean in a minute. Based on that, you can calculate the derivatives on that Bellman operator that is needed for doing Newton's method. And then once Newton's method is really, really close to the solution, well, you can use those derivatives as a byproduct of the algorithm to calculate derivatives of the likelihood function and the fixed point. So it's all described in the manual. Okay. It's a little trivial thing, but you know, look, when you use exponentials on a computer, you put in a big choice-specific value function, especially when beta is very close to 1. Well, these v's are going to be big. Okay, you got big divided by big. Okay, and you know, it grows exponentially big because it's an exponential. So there's a huge risk of numerical overflow on the computer. Okay. So what you can do is do a little recentering. It's you know, theoretically equivalent, and that completely eliminates that problem. If V naught here is the maximum, then all of this is negative. Okay, and then you have maybe potential problems with underflow, but that's not, you know, infinity divided by infinity. You can actually calculate what is the choice problems. The log sum needs to be recentered too, and that's also equivalent to that log sum. Okay, so that, you know, you need to think about numerical implementation and the number of digits where you have precision on the compute. Okay, let's talk about the fixed point algorithm. Now, one of the things you'll see with you do the successive approximations following this algorithm, you start with a guess EV. You know, put it into Bellman operator, get a new guess, and you know, continue, do the value function iteration. Well, that is converging it has this error bound. So you see here, you got linear convergence, and that rate of convergence is depending on beta, and it's really slowing down as beta is approaching 1. It makes a lot of sense. You're trying to approximate an infinite horizon problem with a finite horizon way of computing the expected value, right? So you put a lot of weight on that infinite future. With beta close to 1, well, you better calculate many, many iterations. Whereas the Newton-Kontorovich, well, that would just reformulate the problem. Instead of looking at a fixed point of this Bellman operator, you try to find the zeros of this other operator F, where you essentially just take the right-hand side here, subtract it on both sides, and then you see, you know, get EV minus gamma VV equal to 0. Solve that set of equations just using Newton's method. So you get this iteration scheme instead. So this is the derivative of that operator, and this is the operator. That's just pure Newton. Why I want to do that? Well, it is quadratic convergence. Newton is quadratic convergence. So it means as you get closer and closer to the solution, it's just going to get, the error is just going to get smaller and smaller and smaller in the quadratic rate. Okay, here's a little example. We do the successive approximation with beta very close to 1. You see, at doing 50,000 iterations, it's not converged. Okay? I mean, this should be 0. This is the difference between maximum absolute difference between two successive approximation measured by this tolerance here. Okay? It should be 0, right? Otherwise, the Bellman equation doesn't hold. So even after 50,000 iterations, it's not converged. What you should observe here too is, if you look at the relative tolerance, that this number divided by this number, it is actually equal to beta. That's not a coincidence, and you can show why that's the case. Okay, I'll get there. Okay, so here's a little bit of here's a few graphs where you see the error bound. Well, this number here, you see this error bound is a function of the iteration count. So I've done this for various different values of beta. Okay, so beta is further away from 1, converges very quickly. Beta is far away from, very close to 1, takes forever. You take the log of that error bound, you see why it's called linear convergence. Okay. That's a question.
Yes. Most times, economically speaking, like beta is not going to be very close to 1 because do we have settings where beta is actually that close to 1?
Well, you have very short time periods, like Sucker is working with monthly data.
Okay.
So it makes sense to talk about beta being closer to 1. Okay. What I want to point out is not necessarily that it has to be that it is 0.999, but if you have a model where beta is very close to 1, you better wait a long time for your successive approximations. Okay, but you can do even faster by Newton. Okay, and this is how it looks with Newton. What we do is we do successive approximations until that relative tolerance is close to beta. We shift to Newton-Kontorovich and see here it converged in 4 iterations instead of not converging in 50,000 iterations. Okay, it took 0.003 seconds. So let's hope we can estimate this model. Got the quadratic convergence. Now, Newton is not globally convergent. So you need to get into a domain of attraction. How do you do that? Well, you can use successive approximations. That can get you closer to the solution. Actually, it quickly usually captures the curvature of the expected value function by successive approximation. It's just a constant left. Okay, Newton's just going to strip that constant away. So after a few successive approximations, you are within that domain of attraction, and Newton applies, and you get quadratic convergence. So this is why you want to do this Pauli algorithm. This is just a way of showing the quadratic convergence. And it looks like a Pareto. Here, what you see here is if you suppose you start at the true solution, that's your initial guess, plus just a constant. You already covered the entire curvature of the expected value function. Throw that into the Bellman operator, calculate those, theoretically, those tolerances. If you do that, and here's the math, when you divide those tolerances with each other, you have exactly this relative tolerance equal to beta. So that's a sign that you capture most of the curvature, there's only that constant left. So that's what we're going to do. We're going to switch to Newton where that relative tolerance is close to beta. Okay, so that's just, a summary. This Pauli algorithm. You start with the successive approximations until you get into the domain of attraction. That's when the tolerance is close to beta, relative tolerance is close to beta. And then you switch to Newton until convergence. Now, what you notice probably, or what I'll tell you, is that in order to do that Newton iteration, you need to calculate the derivative of that Bellman operator. Where's the iteration speed? That is right there, right? This is the same as the Jacobian of the constraints, by the way, or part of the Jacobian of the constraints in that impact formulation. Because the Bellman equations were that those Jacobians, and some of the variables were the expected value functions. How do you calculate that? Well, in the discretized approximation of this Bellman operator in integrated value function space, it's particularly easy to calculate those that matrix of partial derivatives with respect to a change in that integrated value function. And it turns out, you'll look at it, it's really just beta times this choice probability weighted transition matrix. Very easy to compute. So it's not like the end of the world to code these derivatives. Okay, this is one line of code in MATLAB. Here's that derivative for Hare circuits model. So sometimes coding those analytical derivatives is actually really worth it, because what is the alternative? Is calculating all those numerical changes to various parts of the Bellman equation when change all these different value functions numerically. It's just going to take a lot of time instead of just this matrix multiplication. And by the way, this is the Bellman equation. You got the value of keeping, the value of replacing. So these are the little v's that are functions of x, and the little d's, the decisions. There's just one for each d. And then here we recenter the log sum. Okay, so to ensure numerical stability. Then if you're asked for it, you can calculate the choice probabilities, logit formula, and then you got the derivatives. Okay, you could do the same thing in expected value function space, just slightly different. Now then there's the analytic gradients of the likelihood. I'm not going to go entirely into all the details here, bore you with that, but trust me, you can do this very simply analytically using high school math. It's a chain rule, you know it, okay? So you want to get the gradients of the likelihood? Well, it's like the standard logit formula, except that now it depends on derivative of these choice-specific value functions. Well, you can calculate those as well, these partial derivatives of the choice-specific values. Well, that's the derivative of the utility function, which is trivial to compute, it's a linear function. And then you need also the derivatives of that integrated value function. Well, here you need to use the implicit function theorem and do a little bit of math, but this is how it looks. You can differentiate on both sides of the equation, and you'll get there. But this is how it looks. What does that depend on? Depends on derivative of the Bellman operator, but we already computed that when we're doing the Newton curvature. It's a byproduct of the algorithm. Okay. So, and from that, you can calculate, then you also need to calculate the derivative of the Bellman operator with respect to change to the parameters. Easy to compute as well. Okay, so with all this, we're just reusing blocks we used before, not to spend time on calculating those derivatives. Yeah. So
I haven't seen it as much for the Rust setup, but I know like in BOP we're also solving a fixed point through accelerated fixed point methods.
You can also solve that fixed point by Newton's method, and there's some of our Korean co-authors. I think they actually did that implementation with the kind of nested fixed point implementation with Newton. So that's definitely.
Do you have any thoughts on like, is that like much worse than this, or?
I would just say if you're trying to solve a system of equation, Newton is usually better than doing successive approximations. Okay, so here's the MATLAB of the scores. It's
I have a follow-up question. So like in the VLP setup, you have some simulations resulting in some discontinuity. Normally, that is
oh, by the way, when you ask questions, it's good if you speak up. I'm cheating, I have a mic, but there's mics all over the place, and the people that are participating online would love to hear what you have to say. Okay.
Do I need to repeat my question?
Yeah.
Yeah. So I didn't think like in the VLP you have some simulation walls, right? So that could result in some discontinuity, making it hard to take derivatives sometimes.
That's actually in VLP, there's a logit-like shock outside that makes the objective function and all of those things smooth.
That's what Whitney actually pointed out here at the end. We do these simulated choice probabilities. Okay, if you do like it's kind of a mixed logit, right? If I remember correctly, you have basically a logit smoothed except reject simulator, where you, instead of taking averages of indicator functions, you're taking averages of logit formulas that are all smooth in parameters. So you can still apply Newton's method there too, if you have the logit shocks. And this is one of the things that this logit shocks is really buying us. Okay, so, well, we got the MATLAB implementation of the scores. We kind of already talked about this BHHH algorithm, that you would like to compute only first order derivatives. That's faster, easier, less to program. You get the approximation of the second order derivatives just by multiplying two matrices. Why not? It's maximum likelihood. Okay. It has the additional benefit. If you're trying to maximize a non-concave likelihood, then if you're using pure Newton to get to the top of the likelihood, there'll be, if there's a convex area of the likelihood function, Newton tends to switch, drive away from that maximum. It's assuming you're doing a quadratic, right? You're making a quadratic approximation to the true function, so it assumes it looks like this, so it doesn't understand what's going on here. You can do step halving and step halving and step halving. You're not going to get towards to the maximum. You're going to move away from the maximum. Whereas BHHH, well, that approximation to the Hessian is always positive definite because you're essentially multiplying, the scores to itself. It's always positive. That's an additional benefit. So BHHH is very, very good for maximum likelihood. Anyway, so I'm not the only guy saying that, okay? It's a way to the top. You want to go to the maximum likelihood. Yeah, sorry about that. And you get convergence. Okay, now let's go back to the point. Is Nfxp really that terrible? Turns out if you implement all these 4 steps, it's not that bad. So here you got the MPEG MATLAB in MPEG Ample. We did the implementations similar to what they were doing. And we get roughly the same computed times and the amount of time it converges as it did in the P. Actually, I think we improved a little bit on it because we were doing the recentering of the Bellman equation that allows us to actually go to 0.9999. Okay, that's also an issue when you do constraint optimization. But look at this; it's the same computed time. So even though this is 35 years old, it's kind of still my Swiss Army knife for structural estimation. It works, and you're forced to think about the economic problem when you solve that model. Turns out if you do sample sizes that are bigger, it actually is faster. So here you got the best implementation of MPEG we had, and the best implementation of Nfxp. And recalculating the results here, it doesn't really take a lot of additional time. It's a time to solve the fixed point that takes time there. That's a bottleneck. That's not affected about how much data that we have. We have like half an hour left or something. Yeah, so I should probably really go fast and just introduce quickly here. This is not the only type of model we're looking at. We're also looking at discrete choices, replacement of cars. And so here, if you want to think about Serher on steroids, read that paper that's coming out in JPE about the Danish car market. Okay, so here consumers, they're making ownership decisions whether to keep, trade, purge, scrap or sell their existing cars. There could be many different types of cars, many different vintages of cars. And then it very much fits into the same framework. Is that me? That says stop. Okay. It's the same type of framework as you've just seen. It's just a little bit bigger model. Okay, so you got the eigenstream value shocks, same types of Bellman equation. Let's just glance quickly over those. Now you will see here, again, you got the expected value function. That's a log sum. Well, those choice-specific value functions now depends on some more stuff, a little bit more complicated stuff. Okay. Well, these various different choices that you have in our model. Here's the choice tree. You can choose to purge your car. If you want to just get rid of your existing car, well, you put it on, you can choose to put it on the scrapyard or put it on the market. Okay, if you want to keep keep your car, you don't have that binary choice. If you want to replace the car, well, you have to think about what car to get. One of those J different types of car, now it's a multinomial choice. Okay, not only that dimension, it's kind of a nested logic, just like Whitney talked about. If you choose a car of type 1, well, you have to choose what is the age of that car. Now that model is exactly the same way, it's just we just did before. It's the demand for all these different types of cars, but at the same time, always get the supply, because if you have a car and you decide to put it on the market, it adds to the supply. Okay. I think I should probably stop here, right? It's John, you need time to go through your stuff.
I guess, yeah. Nice.
Oh,
Sure, take 5 more minutes. Yeah.
Okay. 5 more minutes. Okay. So where should I spend them? This is the way we estimate this model. It's a little bit, there's an equilibrium calculation here, because the prices of these used cars, you're not holding those as fixed. These are equilibrium objects. Okay? These are the prices that put supply equal to demand at the used car market. Well, that's determined from the discrete dynamic programming of all these consumers that you have. Okay, so if you want to estimate this model, it's no longer a 2-ring circus where you have the hill climbing algorithm outside and the fixed point algorithm. Now it's a 3-ring circus. There's also an algorithm in the middle where you try to find a stationary equilibrium in the market for cars. Okay, so what you do is you maximize the likelihood, but every time you maximize likelihood, you find the prices that put the excess demand for all these different types and vintages of cars equal to 0 to calculate the excess demand. How do you do that? Well, you solve all these fixed point problems by Newton's method, Newton-Kontorovich, just like we did before, okay? And then from that, you can calculate the stationary distribution of car ownership from the transition matrices that are implied by all the choice probabilities. Okay, so and given that, well, that's what you put into your functions of excess demand, and then all of that depends on prices. You search for the prices that put supply equal to demand. Okay. And by the way, all the code and data for this paper is also available in the box, so try to take a look at it. What are we using this for? Well, we estimate the model on Danish register data on 40 million observations, a lot of heterogeneity consumer types. It fits pretty reasonably well. And then we do a little counterfactual analysis for this model, try to change the taxes. Turns out in Denmark, taxes are so high, we are way above the Laffer curve in terms of the registration tax. We pay 3 times the amount you pay here. Volvo is like $200,000 in Denmark. It's in Denmark, whereas here you probably get it for 60,000. Yeah, I think I should stop here and give the floor to you, John. Sorry for not making it to the end. There was 113 slides. It's probably too much.
I need the
So Mike?
Like, okay. And you take that. Yeah, so I think we like to spend more time on that auto paper. It's an example of counterfactual equilibria, right? And we are, Denmark hasn't changed its car tax yet, and so there's no, there's no way. How do you do that except through a counterfactual experiment? Now it's possible. Alberto Abadi talks about synthetic controls, and you might reweight the Danish population and compare it to Germany and England, which have lower car taxes. But so it may be an alternative. But our paper predicts a big welfare gain, we actually, it's just a win-win situation. You lower this car tax, you raise the gas tax, and you lower CO2, you make consumers happier, and you raise more money for the government. So through this counterfactual analysis, we find a better way potentially. So, but I'm going to pivot, and it's a little bit risky, I guess, what I'm going to do, because I'm going to talk about work in progress with Harry Parsh, who will be talking tomorrow on auctions. But and this is the title of the paper we're working, it's work in progress. So, but I thought it might be interesting because, you know, we're right in the heat of doing this thing, writing up our results, and getting feedback is really good. And I can also, tell you some of the problems we're having right now and some of the troubles. So you're seeing research, and I'm trying to teach you research by doing it. So, so what we're looking at is a bunch of, this is also with co-author Sung-Jin Cho at Seoul National University, and he got data on a rental car company that sells its used rental cars in online auctions that last 2 minutes. And so these are 2-minute continuous time auctions. And if I have time, I'll actually play this auction with you right here. We're gonna bid in one of these rental car auctions. It's a simulated auction, right? And with computerized bidders. So we're gonna bid against them and we'll see how we do, right? So if we have time, I'm gonna do that. But this company designed this unique auction format because it was worried about collusion. They used to sell their cars kind of on the lot in, they're called open outcry, where a bunch of people stand in, they would say, I'll bid 5,000, I'll bid 6,000. And so that's called an ascending bid open outcry auction. But they were worried about collusion. And so they decided to design this online internet with restricted information. So I'm going to show you the restricted information, but basically during the auction, you don't know how many other bidders are there. You don't see their bids. You only see your bid and whether you have the highest bid at any point in the auction. So it's much reduced compared to an outside auction. And the idea is maybe they're signaling each other with their bids. So we decided we wanted to analyze this. And the point here is, how does it relate to what we're just talking about? We're using dynamic choice theory, but now not just discrete choice. This, so during these auctions, you have any point whether to bid or not. That's the discrete choice. Then there's a continuous choice, how much to bid. So if you decide to bid during the auction, how much do you bid? You bid a little, or so that's a continuous choice. So we want to take what Bertel was showing you and extend it now to discrete, dynamic, discrete, continuous choice, and then see, can we model the dynamic bidding that we see in an auction? Now, I want to just relate this to the market design. So how does this all, the reason I wanted to do this, I think, well, this is relevant to market design because, well, first of all, auctions are markets, right? They're small markets, where when you have only 5 or 6 bidders at a time, you can affect the price, right? So there's strategic dynamics, and you don't want to overbid all the time, right? Because you could affect the price against yourself. So the idea, and if you think about the first application of market design, there were optimal auction design, right? And so that's a classic example of market design. And there's all these different formats, which Hario will be talking about tomorrow, like the English auction, the open outcry. That's an example of an English auction. But then there's a static format called the first price sealed bid auction, right? You just write the value on a paper or submit it over online at one shot, and then whoever has the highest bid wins. So, so then, there's these, and then you could also think about non-auction methods, like having a lottery. You buy a lottery ticket, they hold a raffle, and then whoever gets it. So there's all these different mechanisms, and I've always thought this is very cool, to look across all these mechanisms. Now, there's just an unbelievable paper by Roger Meyerson in 1982, right? It's Optimal Auction Design, where he designed the optimal way of selling a single item and it turned out to be an auction, but it could have been any, he talked, it's kind of the part of the birthplace of mechanism design. Think about any possible way of selling this item what's the best way if you want to maximize the revenue for the seller? And what he showed is, and there's a lot of side, beautiful theory, including the revelation principle, the idea that you could just formulate this as what's called the direct mechanism, where you just tell your value, but tell it truthfully, right? So you want to truthfully reveal your valuation, which most mechanisms, you never want to do that. It's really dumb to reveal what you really think something's worth. But he showed you could restrict it to a search of within direct mechanisms. And so that's what's called a Vickrey auction. A Vickrey auction is called a second price auction, where you bid, but the winner doesn't pay their bid, they pay the second highest bid. And if you think about it, in the second price auction, it's dominant to be truthful. You just simply bid your valuation, and then the highest bidder wins it at the second highest price, right? So, this is done under what's called independent private values paradigm. And, he designed this, and then it's a Vickrey auction with a reserve price. That was the optimal, if I got that right. Now, this Vickrey auction, it was actually invented way before Vickrey first analyzed it. So that's when the second price auction was analyzed in 1961. You got the Nobel Prize for that. But according to Wikipedia, this had been around since a long time before that. They've been using that a long time. But their more modern theory looked at something called revenue equivalence, and they showed that, well, a second price, if you have symmetry, the first price and the second price auction generates the same expected revenue, right? Now, the only thing is when you do all this theory, it's really, really cool. It's really easy to be seduced by it. But if you look at laboratory experiments on the second price auction, what you get is overbidding. Like, people think, wow, I don't have to pay what I bid. Well, then I can just bid a lot more than I actually think it's worth, because I'll maximize the chance that I win. And that's been a systematic finding. So this is like an example of a paper by Cooper and Fang. And they cite all this previous work that's robust, where students in laboratory overbid for the auction. So there's a behavioral element where people are not fully rational. So then you think about, what does that imply for market design? Should we not, if maybe first price auction is revenue equivalent to a second price auction, but if people are irrational overbid, maybe the auction designer should have a second price auction and use all this animal spirits and get overbidding. They'll get actually more money than they would get in the first price auction, right? Now, but then you have to be a little bit careful, because there's an article by Paul Klemperer. It's what really matters in auction design. And he says, economists are very proud of their role for pushing for auctions. For example, Coase was among the first to advocate auctioning the revenue spectrum. But many auctions, including some designed with the help of leading academic economists, have worked very badly. So he gives an experiment, I think Harry can confirm this. In Australia, they were using the second price auction to auction offshore oil leases. And there was collusion by the bidders, and someone was offering $1 million, and then the next highest bid was $1. So in one auction, but the second, they're selling that auction lease for $1. And then on the next one, they just flipped the roles, and then one guy bid, $1 million, and the other guy bids $1, and they're selling all their oil tracts for $1. And it looked tremendously stupid. And when it got out in the press, like, these dumb economists, what the heck are they talking about, right? So collusion is an issue, right? So collusion, when you think about market design, you have to think about irrationality or hyper-rationality or kind of collusion, and you want maybe something to be robust in terms of both. So then you want to think about kind of robust mechanisms that tolerate deviation from rationality, that may, there may be presence of collusion of some form. So, and this involves, you can't just do Roger Myerson. If you talk to Larry Ossibel, I'm a friend of his, I used to be a colleague of his, he said, how important is mechanism design? He says, not that important. For him, it's judgment and understanding the auctions. These guys actually design the FCC spectrum auctions, right? Which are unbelievably complicated auctions, dynamic ascending bid auctions combinatoric because you can have different bands of frequencies. And in fact, nobody can solve these auctions. These auctions are so complicated. When they first designed it, people didn't even know, could all these sophisticated companies like Verizon and AT&T actually even successfully bid, because they were so damn complicated. But yet, you know, people are bidding in them and they're actually raising billions of dollars for the government. And the objective is not just to maximize revenue, but it's also to actually create good competition and social welfare so they're trying to balance these things. So, you know, this is just, you know, mind-boggling, right? And what's really cool is economists like Larry Ausubel, like Paul Milgram, they are actually, you know, they're under contract, and economists are actually designing markets. So, you know, I often feel very useful at this, but I look up to these guys and say, wow, these guys are not just taking the theory and they're making it reality, and it's changing our society in some sense. So that's very, very cool. So that's why I always, you know, like it. Now, how much time I have? Well, I just want to mention, and Harry's going to talk about this, but there's a cool article by Satterthwaite and Williams. These guys are also really, you know, I think Satterthwaite should get a Nobel Prize sometime, and probably Williams too. You know, L. Roth, by the way, you know, the other kind of a market design, it's L. Roth, right? And kidney exchanges and thing got a Nobel Prize. So these are all Nobel Prize, but they've done really good work on something called the K-double auction. So, you know, normally think of an auction, you're selling one thing, but when you're trading things like in a stock market, a K-double auction is, you know, for instance, here's a simple, with a finite number of buyers and sellers, and you get discrete supply and demand curves. So if these were their true valuations, you know, some buyer values at 1, the next 0.8. And if you array the valuations from high to low, the true demand curve would be the step function and true supply, and then the equilibrium would be, there would be a tunnel, there'd be a range of prices that set supply and demand. And the K-double auction is very, very simple. It's like a sealed bid auction. You just reveal, you just say what you want to pay for as a buyer, and then as a seller, you submit an ask, how much you want to sell it for, and you just rank the bids and the asks into reveal supply and demand curves, and then you would pick some number in that equilibrium tunnel. It could be the top one, the bottom one, or the middle. And K denotes what fraction. K 1/2, it's in the middle. K 0, it's down at the bottom, and so on, right? Now, what they show is this mechanism is robust in a computer scientist setting. And it's kind of worst case optimal. What they show is that the incentive to lie, to shade your bid or ask disappears very, very rapidly, like order 1/n. If there's n buyers and sellers, that incentive to lie deviates goes to 0 by at rate 1/n in the worst case. And so that essentially you're optimally, you know, even in very small markets, you're just revealing the real supply and demand curves, and you're getting the Walrasian solution, a fully efficient outcome. Okay, so and in the conference we're having this week, Pete Kyle and Peter Crampton, they're proposing that we run our stock markets this way. Instead of having this race, this arms race with these things called limit order books, they say change the market design and have batch auctions like the Satterthwaite Williams. Every second, allow bids and asks to arrive, then they just rank them, cross the supply and demand curves, get a price, and just do that in discrete time intervals. And you would completely eliminate this arms race for trading on the stock market and get a much more efficient outcome. So this is stuff that's very, very relevant to what we're doing. Now, the other thing I just want to say before I go back to Korean rental cars is, you know, static versus dynamic auction mechanisms. So another way you can play this game is not through static, but you can play this in continuous time, right? The continuous time double auction, there's been thousands of laboratory experiments, and humans can play this like for 2 minutes, and you can either play it like open outcry and, you know, calling out bids and asks, or doing it on the computer. And guys like Charlie Plott and Vernon Smith have done thousands of experiments, laboratory experiments, and they reliably find that the price kind of moves in a jagged way, but it converges to equilibrium, and the outcome is very, very efficient, close to 100% efficient. And so that seems to be another robust but dynamic mechanism. So the question is, what's better? Should we use a static mechanism or should we use a dynamic mechanism? And Harry's going to be talking about those tomorrow. There is something, though, that's called the linkage principle. And when there's kind of not independent values, but common values, that like in an oil auction or something, or like an FCC auction, that you want to have it to be a dynamic auction because information is revealed along the way that helps people learn about the true value. Their values are not, completely fixed as they come in. They learn from each other in the bids, and that by doing it dynamically, you're going to get higher revenues and higher bids than if you did it in a static way. Okay, so let's see how much time I have. Now we're going back to Korea. Okay, so I have 5 minutes. I'm going to show you some actual auctions. Okay, this is kind of fun. And then I'll see if I'll try to play one of these auctions. But here's the auction. So the idea is to prevent collusion. You can't see the other bids. And so what that does, so this is one auction. It's going for 120 seconds. And these different symbols are the different bidders. Now, you would never see in an open outcry, if everyone said everyone bids, it would make no sense. The star there, they're bidding below the highest. The red is the highest bid, right? Well, the reason they're bidding below is they don't know what it is, right? So the person in the star, bidder 5 at around 58 seconds, bids low. He has no idea what it is, and then he's informed that he's informed that he's below the highest, and so then he's creeping. He's bidding up higher and higher until he gets the highest up there. But then someone in the triangle bids him out, and then the light goes off on the screen. He knows he's no longer the highest bid, and then he makes one more bid, and then makes a few more bids and gives up. But in here, this B41 wins just at the very last instance. B41 enters there and wins the auction. Okay, now let's just show you another example called bid sniping. This is there's been articles about this. Now, what's sniping? That's when somebody comes in, doesn't bid at all during the auction. This is the winner here is this one with the red dot, B3. You see, there's no red dots. B3 just comes in 118 seconds, makes one high bid there, and wins the auction. So they enter at the very last minute. Now, this is kind of an advertisement. I'm going to complete this lecture tomorrow after Harry has given you some auction theory, and we're going to go through this. But let's just play this auction now and just see what it's like to play it real. I'm going to play it against robots. So I have some software up here. You see this? We're going to play. It's called Play Auction. I'll make the software available to you. And I'm playing against actually structurally estimated bidders. So I'm going to tell you about how we estimated these bidders. And so these are kind of robot replicas of some of the bidders in these auctions that we use real data to bid to create robots. So no, I've been allocated a price of $7,000 on this auction. So I believe I'm going to buy a car, and I think it's worth $7,200. So I'm going to start bidding right now, and we'll show you what it's like to bid strategically. And then I want you to think about tonight, seeing this auction, how would you write this as a dynamic program? What would be the Bellman equations? And then how would you implement this with data if you had this kind of data? And tomorrow I'll show you how I did it, but this then shows you you start with the idea, the economic intuition, then you turn it into the math and then try to simulate. So right now in this auction, what would you do? Should we bid right away, or should we just hold, you can stay out. If I hit the return, so there's my valuation, 7,258. And seconds are going by. So here I'm slowing down time. So I can run this under a timer, but that makes it too much of a rush. But I'm just seconds are going by, and I'm saying I'm not going to bid. But hey, should we make a bid? right? We think it's worth 7,200. So what should our first bid be? Anyone want to call out a number that we want to bid? Should we bid 500? Should 500 be too much? Let's try 500, see what happens. You're not the high bidder. Okay, somebody's already been bidding. Okay, so we learned something there. We're not the high bidder, so somebody's already bid more than 500. So now what do we do? Now the question, what's the pros and cons? If we bid higher, what if I say, well, 1,000? If I'm kind of a little bit too greedy, I'm curious. I'm saying what it is. Is it 1,000? No, it's already gone above 1,000. Now the problem is, to what extent that if I try to learn what the high bid by bidding higher, could I push the other people better too? So once I get above, maybe I'm actually pushing things against me. So there's a trade-off. I want to learn what the high bid so I don't overbid. But if I bid too fast and too aggressively, I could shift everyone up also and end up paying more than I would like in a first price auction. So anyway, let's go. So let's be a little careful. We'll let some seconds go by.
What time is it now? In the 27th, what?
27 seconds have gone by. So I'm slowing down. I'm making it discreet so I can talk, but I can put a timer on this and then the auction will have been all over by now. But now let's jump to 3,000. Let's see where we're at. Man, it's not, they've already gone through about 3,000. So I'm getting pessimistic. Maybe they all think the car's worth more than I do. Let's go to 4,000. Oh, all right. I'm the high bidder now. So now at 36 seconds in the auction, I know I'm the high bidder with a bid of 4,000. Now, what should I do? Should we hold or should we keep going up at this point? What's the rational thing to do? Hold. Yeah, right. Let's just see how long I stay. Oh, within a few seconds, now 30 seconds, someone's already bid over me. All right. Now, did I cause somebody, that they were neck and neck, and did I cause them to go higher? Should I hold for a while and then enter later? So let's just hold and be patient. And I'm just going to let a few more seconds go by. But now I'm curious again, what should we put in now? What number should we put in now if we want to try to learn what the highest bid is? Anyone want to shout out a number? Should we go up to 5,000 or is that too much? Remember, we think it's worth 7,200. We want to make some profit on this. What number should we go for? Should we go to 4,500? How many think? Let's try 4,500. You are a high bidder. Okay, so now we're at the high bidder at 4,500. Let's stay there for a while. 60 seconds in the auction. Somebody's beating us now. So I'm gonna leave on time. No, I don't want 50,000. I want five. Let's go up to 5,000. I had a suspicion. I don't want to get too fast, get up there, but no, not now. They've already gone ahead of 5,000. So I'm going to hold off. Now we have 120 seconds. Now time is running out. How about we go up to 5,500? All right, we're at the high bidder at 5,500. Okay, 99 seconds into the auction. You are the high bidder. We're staying the high bidder. Hey, maybe we can get it at 5,500. Going, gone, right? We keep hitting it. Let's see if someone jumps over us. 150. Somebody bent over. Now, maybe we shouldn't go up on 500. Let's go to 5,600. 5,600.
55.60.
55.60. Okay, 55.60. Yeah, maybe you should bid like a prime number or something, right? You're not the high bidder. Anyone, should we go to 5,600? 5,600. No, 5,700. No, we're creeping now, right? We're doing what's good. You are the high bidder with 57. Let's. All right, 2 seconds left. Now we're really talking turkey. Now we have slow down and think. We're not the high bidder, 57. We got two more chances at second 119 and 120. So anyone want to offer what bid should I make at second 119? Anyone want to suggest? So remember, we think it's worth 72.58. If does anyone have a strong feeling? How high should we go?
You should be your best.
Should we go to 6,000? And 6,000, is that too high? How about 5,800? Okay. You are the high bidder. Okay, now. The high bidder, we can hit return and hope we win, but someone might be sniping on us. Remember, we saw the example of sniper. Should we go a little bit more? Should we go to 58? Because we're still making a lot of profit, right? Should we be greedy? 58, 72 minus 50, that's a pretty good profit, right? So what do you say? Should we hold? How many people think we should just hold at 58 and just press the button and see what happens? How many people think we should go up a little higher? Anyone want to? Okay, okay. So how much should we go to 5,900?
58,000.
5850? All right, let's do 5850. Let's see. Now this, I'm going to hold you responsible.
This is why I can't gamble.
Congratulations. All right, now let's take a look. Now, I am comparing myself to a computer. And I will show you.
Yeah.
We won, and we made a profit of 1408. Now let's just see. I'm a little bit. I'm 5 minutes over, so I'm sorry. But let's just show you these numbers here. If we had sniped, I'm going to show you these numbers with this. Where's the green thing? We have a calculation from my dynamic program that the optimal, if I would have played in a first price auction, I should have been 5,900. So we bid a little bit less than that. And the profit I would have gotten in the first price auction, so we did better if I would have tried to snipe. If I did sniping, I would have, or in the first price auction, I would have won with 56% according to the dynamic program. Now, if I would have bid optimally dynamically, my profit goes up to from 727 to 1859. So actually, we didn't do as well as what the expected profit that the computer would do. The computer would win with 84% probability, and conditional on winning would get 2,200 versus. So we didn't do as well, and the computer would on average would have won at 5,054. So we overbid relative to the computer. And then finally, I'll show you our auction outcome on this. This is the similar graph that we saw for the real bidders. Looks like our computer bidders looks kind of like reality. Okay, so there's math underneath here. We'll show you more about that next time, but I just wanted to show you how the game's played and just getting you thinking. Then now let's just think about two mechanisms: the dynamic mechanism versus the static mechanism, first price auction. What would be better for this guy? And is one more susceptible to collusion than the other? So we're going to come back and ask those questions next time tomorrow after Harry tells you more about auction theory. So sorry for going over.